Okay, so welcome back to our session. So our session. So first of all, we will give Professor from Tsinghua some physical big data. So let's welcome.
Good afternoon, everyone. Hope you have a good lunch. So actually, I'm thank you for the organizer to give me the opportunities to invite me to the talk. Actually, it's in Harvard, so I'm honored to give a speech here. So basically, this my early project started in one back Tsinghua. I got a project called NetSense project. This is talk about cyber physical human big data computing. So I'm going to talk about a little bit. This already go through 5 years, so probably something probably pretty old nowadays. So basically, the first I'll talk about what CPH. I think in the US mainly talk about CPS, cyber physical system or cyber physical society kind of system computing. Then in China, to promote cyber physical human computing, so H stands human. So talk about next what is about. So talk about associate with the CPH computing, what's the scientific problems, what problem we are addressing now. And specifically, I only talk about one problem, which is how to do the heterogeneous network representation as an example. So it's only 15 minutes. So this is all data is everywhere, so I'm going to have this slides. So CPH, basically, I think for people know very well cyber physical. Cyber means internet of data, and physical means all the different kind of sensor data. Then for the human, actually, when we go to the artificial intelligence AI stage, we realize the human is very important. So basically, these two, for this project, we do the mapping between cyber and physical. So basically, when you have something online happening or something, we have to check offline. So what we can see, not only look at the virtual world, in cyberspace, mostly the virtual world. We see something happens in the internet or online, then we have to check physical world what happened offline, or in the real world what happened. So the difficulty of this is that we need to find mapping data alignment between cyber and physical, the two spaces, cross-space mapping. Then put a human there, it means human have knowledge. So knowledge can guide this mapping. Without human knowledge, without human, we call wisdom crowd kind of knowledge, then this one only in data plane, we can call it in data plane process of this two. Then mapping. Then in the knowledge plane, we can inject knowledge to guide this data mapping. So this is the key idea of this CPH computing. Then the key is first of all, to need to find the correlation between the three cross spaces. So mainly is the cyber physical two space cross correlation to find the correlations of data mappings, alignment of this sometimes called. Then once we got that, then we need to first understand from data plane we call data knowledge. Then second, we need to using the human knowledge to correct or to see if the data knowledge to add to our new knowledge or not, or is consistent with our human knowledge or not. So this is the key of this. The first problem actually is representation. So how when we do cross-space or cross-domain representation for heterogeneous data, how we do representation, I think this is the first problems. So basically, it's so this morning also for a talk about the multi-channel data. So basically, nature is a multi-source, multi-modality data in nature. Then it's cross this time is changing. Also, you talk about correlation. I think about scale in space domain. How the thing. So basically, the challenge of this is that how we find representation. Historically, people do this homogeneous representation very easy. So we find a feature space. We usually call feature space. Then we project all this everything to the feature space. So we need to call common space. So this is the traditional approach. We're using the features. For example, if I have images from this internet. I also have photos from real world physical space. That's all same feature, because all images. But when we do different homogeneous representation to find feature space as a common space. But once we do the strong heterogeneous data, which is sometimes we have a physical location, for example, then we have we know what event will happening, what time and what space, what location, what event will happening. So this is a kind of representation how to do. So first we cause the problems need to be solved actually. Then the challenge for this is that actually for small data sets, people do very well on representation, which means they're using prior knowledge a lot to solve this representation. In the big data stage, actually, the prior knowledge is not easy to be added. So we just found that the difficulty is that in the week prior, how we represent data for this homogeneous data. That's one of the difficulty we have. Our idea is that actually we do using representation learning is multimodal heterogeneous representation learning to learn a hidden space. So the hidden space, which means not like before, we know beforehand what feature space is. So basically, it's a machine learning. So learn a mathematical representation. Then we got correlation of their in the hidden space we find their common representation. Then we're using data mining technology to find their correlations. The second problem actually is that what kind of if you use a data-driven approach using machine learning, the results is not is well explained. This morning approach. I'll talk about explainable AI. So basically, if we only rely on this on the machine learning data-driven alone approach, then the results will not be accurate or may not be what we want. We all even don't know the result is correct or not. Then usually humans have knowledge to judge the data is correct or not. So basically, how we get knowledge? Then this word actually in the computing area, this one is still new. So crowdsourcing word is very studied, which means if we have a computer task, we divide too many small tasks, then we get each in parallel get done, then we assemble it back. So basically, that's crowdsourcing. But this is wisdom crowd means if you on the knowledge level really doesn't have good method, really everyone has own ideas, then you have many people how we get new ideas. So this is one very difficult. But the question is how we can using a group people knowledge to judge for this. So in real world, when we do, for example, when we get a patient, sometimes one doctor says this way, sometimes in China we assemble a group of doctors. So similar that kind of idea. But the key is how we're using computational model to build this one very difficult. But we haven't, even for now, we haven't gone much far on this. This is collective learning or how we human learning. So it's very difficult for this one. This is beyond a data-driven machine learning. So this one, we don't have make much progress even now. But the idea we proposed that time. So the idea is that today, what we can do is that we can using a knowledge base or knowledge graph. So basically, we have a timely update that graph. It's a knowledge-driven thing. Then we have machine learning, data-driven thing. We can get results. Then these two can be joined together to see how this knowledge can correct what machine has been done. So that's the key second problems. For this one, actually, we learned from social science is that for data-driven approach, we always have a big scale. Computer can do as much height dimension as billion scale level data to be processed. But the explainability is very low, and even it's very high actually. But so from social science, actually, when they only keep track of maybe 100 people at one in hospital, the doctor will track 100 people at most. that even in the society, when if they are want to do their PhD, they only take a couple of years, only track a few people. But that is all real science. So it's not computer generated thing. So this one has very good explainability. So the question is how we got balance. We can take advantage of computer science advantage is computing fast, computable, but in the meantime, how we also get human social science advantage that everything is explainable. So that's a very hard thing. For now, actually, the key thing we still using cross-sourcing name. Because with cloud computing today, we can't go that far. So we still using that model. We can, if we want to get that model, actually, they can help us a little bit. So basically, then once we get the cross-sourcing model, which means that we need to find for example, not a graph kind of thing. This is you can think about that is a kind of the model we generated. Then we have a knowledge representation. We can get knowledge representation from this or knowledge base as this. So we can correct what we have done using machine learning results. So we can using plus so get fused results. So we think this way we can get a better. So this is very high level overview. So next, I only present one thing in the next 5 minutes is that if we have multimodality data, how we do representation. So in real world, actually, all the data can be represented as a network or graph. This is for the graph. Well, I think for graph data or network data, the key thing is that we have a coupling effect. So we have hyperlink, sometimes preventing us to do the big scale or large scale machine learning. So because they have coupling effect, they have dependencies, they have so it's very difficult. So basically for a graph, we have a node and an edge and link, and a node and link. So basically the question is, we do network representation, I will call network embedding. What can do? So basically, this is go to a low dimensional vector space. So this means if we can do a large scale graph, we already determined go to the billion scale graph, levels graphs. Then we can vectorize as see all the edges are gone, only have nodes. So this way we can apply machine learning in large scale to this vector space. Another advantage of vector space is that it's very studied and also hardware integration very easy. And this is one way to do this. But we do the best how to lose as little information as possible. This is the whole thing, the embedding thing. You have advantage to vectorize data graph, and another thing is that how we treat can keep less loss of data. So basically, this is one approach. This is the first approach to present using deep neural network to do the this network embedding. So basically, people know that before using vectorization to do the embedding, before this work, then vectorization only can capture this first order relation, or called linear relation sometimes. But in the social network, we have second order or high order relation. This means I don't know Professor Liu, but I know Professor Liu's friends. That this is the second order. So even sometimes have high, even third order or fourth order. So basically, this way, deep learning has the advantage of nonlinear can capture this high order similarity relations. So this way we can formulate it as fourth order. We call local relation. Fourth order is a direct connection of the graph. So we can capture this network embedding. Basically, the difficulty is how we keep in the mapping new mapping domain, how we keep this structure not change. Because structure preserved embedding. So basically, once we need to keep a first order structure, we also need a high order or second order structure. Then we use deep learning and can keep this part. Matrix this only can keep the first order. This is the idea of this. So I will not go to this deal. This is the KDD data mining conference, ACMKDD, on 2016. This paper was widely cited. It's already in just 3 years over 600 citations already. It's this first work to using deep neural network to do this network embedding. For this one, actually, is for the heterogeneous hypergraph embedding. Hypergraph means one node could be have different attributes. Heterogeneous means that we have multiple data for each node. Then the hypergraph, which is usually we have tuplets. So basically, before this work is pairwise, means any 3-level coupling relation can be all decomposed to pairwise relations. For example, if I know time is one dimension, I have location is another dimension. The third dimension is the event. Want to see what time and what space what happened. So this is triplets relations. So previous work is that you decouple to the pairwise two relations. So they can do time and events. They can do this very well on this location event. But once triple together for graph, how we do embedding doesn't have such kind of work. So the key thing will be this decomposability problem. Also, data is always sparse. So this is how we do this. So basically, we also use to see, we studied that we propose a function called a tuplewise similarity. So for triplets relation, how we define a similarity function, then we prove that this function is nonlinear. So triplets can be modeled as a tuplets similarity function. That's a nonlinear proof that. Then this is one we can use deep neural network. Since it's nonlinear, deep neural network is always better than matrix. So basically, then we design a first order and also second order, higher orders. So using a decoder to present this. So it turned out to be that this work can solve the hypergraph embedding problem by defining this. We call it tuplewise similarity function. And also using first order structure preserve similarity approximation. Also using second order. So we using both. So I think my time are out. So basically, today I briefly talk about what's cyber physical human big data, how we doing that kind of thing. Then this key thing is that for this is the two key things actually. One is heterogeneous network representation for the multimodal heterogeneous data, network data, how we do the representation learning. Second one is that we tune a little bit because today we cannot do wisdom cloud computing. With cloud, the concept actually is a common science guy. Think about how to computing humans' wisdom. It's very difficult because it needs a computational thinking kind of modeling, which is very difficult to be modeled. I think Harvard has such kind of environment to do this. Not many places can study this kind of model. So basically, when we tune a little bit, we use knowledge to knowledge means you can knowledge base, you can knowledge graph, to guide it to supervise the machine learning method. Otherwise, the machine learning method is just a machine doing things people don't know correct or not. Then I only give one example today to talk about this this network implementation learning. Thank you for your attention. I'll stop here.
Okay, great job.
Professor Zhu, it's a very interesting talk. You talk about the paper in 2016.
16, that's this one.
Is that possible to model any other information?
Yeah, we have that's one already done. That's I don't have time. So basically, in 27 we have another paper talk about the arbitrary order network embedding.
Okay.
Zvi did that. Yeah.
So what's the difference to the graph convolutional?
Actually, I think they use it's not a line. It's a line. They're using different combined with deep learning with with matrix. But that one, actually, the detail I don't know. Actually, I'll be honest. I would like to take the question and send a paper on a student's answer. That's why I didn't go through that.
Any other questions? Yes, Professor.
So you use first order similarity, second order similarity. So the first order seems more accurate. The second order, a lot of noise may be introduced.
Yeah, that's smart. We use regularization. Regularization added as a regularization term. So for second order, once you formulate this Laplacian, this one, this is you said you're right, because second order is noisy. So we add regularization plus lambda, then you have regularized term to regularize this second order. Otherwise, this is.
So in that case, second order also can improve the accuracy or something.
Yeah, because
how about the third order?
Because this is particularly for social network is very effective. Because social network, not everyone has a direct connection among nodes, social relationship. But sometimes people have second order. So this is means we know someone in common, but we don't know directly.
Yeah,
third order, so this higher,
yeah.
then this can capture more of that correlation. But I agree with you, when go to higher order, then the sparse, even sparse. Because
maybe negative influence, maybe. So if the third order, you consider third order, so
you have two papers just now.
Also always positive or negative.
I think good question. So far, I think the second order most time pretty good. When go high order, the incremental very small because not relation very complex. Even access, even sparser and even noisier the data when you go to the different relations.
Okay, let's thank you, Professor.
Thank you for your attention.
So next speaker will be Professor Wenwu Zhu.